Hello, everyone. I'm David Sayre. I'm the lead of the Mountain View Android Runtime team. We're the folks that build the code that runs on your phone and loads your applications, runs them, and manages their memory. So last year, our team presented the evolution of art, and we described some of the techniques we're using in the runtime and how you can really see the goodness that we bring. Last year, we talked about profile-guided compilation, how you can make your app experience better by understanding how programs run on your phone. We talked about how important it is to keep memory usage down and to make memory allocation blindingly fast. And we talked about just-in-time compilation and how we can get great performance from your applications without the annoying optimizing dialogue. So you heard last year about how great things are, but it was just the beginning. Now that your phone knows more about how your applications execute, we can focus on loading only the parts that are important to you, so apps load faster and use less memory. And speaking of less memory, we've made your applications spend less time reclaiming and even less time allocating memory. And of course, with the just-in-time compiler, we can focus on making your applications run even faster. Nicholas and Art will be talking to you in just a moment about that. You'll notice I mentioned using less memory twice. So let's start by talking about that. I'm going to begin by talking a little bit about how we rearrange your application to use less memory. And then Matthew is going to tell you about how we improved our heap sizes, reduced the jank, reduced the pause times, and have even better allocation times. First, a little review of how Android applications work on your Android phone. An application comes in an APK file, which contains one or more DEX files. These contain the instructions for executing your application. Art uses the DEX files to get information about instructions to run, strings, class relationships, and lots of other things. And the DEX files are loaded into memory by Art. Loading these files has both a RAM and a startup time cost. So when you run, for instance, Maps, one of our favorite applications, your phone reads the DEX files into memory, and you can see amounts to thousands of pages. Multiple megabytes worth of information are loaded into memory. Now, the DEX files were produced by a developer, and the typical developer tools don't really know about the use cases that are going to be important to you on your phone. So the DEX files may have unimportant things on the same pages as important things. Like, for example, the way you use Maps, you may only use some of the methods that were in the DEX files. Or some of the strings that are there are not seen in your use case. As I told you before, in Android N, Art introduced profile-based compilation. In Android O, we have clever new uses for this. Several clever new uses, in fact. But one of the ones I'm here to talk about is improving the DEX file locality. The idea is simple. Use the JIT profile information to move the important things, the things that have been used by you and your usage of the applications, closer together. And this is all done seamlessly and transparently to the user as we compile applications on the device. So after we run your application once, at least, to collect the profile information, we use information about what parts of the application were important to you. We gather the important methods together and leave the unimportant methods together. And as you can see on the right there, a lot fewer pages are accessed, especially the methods, when we use profiling information. Now let's take a look at what type of RAM improvements we see after launching a few apps, a few of our favorites again. As you can see, there's a significant reduction, typically around a third in these applications, less memory used by DEX after layout. This RAM reduction also improves launch time on devices that have slower flash because you're pulling in fewer pages and hence spending less time paging applications off of the flash. So that's it for my part. Now over to Matthew, who's going to tell you about our new garbage collector.
Thank you, David. Another thing that saves RAM is a new concurrent and copying garbage collector. Now, Android has had a compacting garbage collector that runs for background apps since Android L. But unfortunately, since this collector was non-concurrent, it meant that there was a GC pause for the entire duration. So basically, the problem with having a GC pause for the entire duration of the GC is that it can last hundreds of milliseconds, and this would very likely cause jank for foreground applications. In Android O, ART now concurrently compacts the heaps of background and foreground applications. This enables compaction of many long-lived applications, such as the Android system process and Google Play services. Since these processes were long-lived, they tended to have a high fragmentation over the time that they were executing. Let's take a look at the GC process. Unlike its predecessor, the new GC is region-based. Starting out, the GC does a brief pause to identify which regions we are going to evacuate. These regions are also known as the source regions. Threads then resume from the pause after having walked their stacks. Next up is the largest phase of the GC, the copying phase. In the copying phase, reachable objects are copied from the source regions to the destination regions. Finally, in the reclaim phase, the GC frees the RAM for the source regions. Starting with the pause phase, the pause is pretty small, and during the pause, one of the key steps is identifying which regions to evacuate. The goal of evacuation is to copy all of the reachable objects out of regions with high fragmentation. After this is accomplished, the GC can release the RAM for these regions. In this example, the GC picks the middle two regions as the source regions because these both have more than 20% fragmentation. Next up is the copying phase. In the copying phase, the GC copies all reachable objects from the source regions to the destination regions with the goal that no objects will reference the source regions after collection is completed. The GC also updates the references to these regions to point to the new addresses of the objects. Now, since application threads are running concurrently during the garbage collector, the GC needs a way to make sure that these threads don't end up reading a field that points to a source region. To accomplish this, the GC uses a technique called a read barrier. A read barrier is a small amount of work done for every field read. The read barrier prevents threads from ever seeing references to the source regions by intercepting the reads and then copying the objects to the destination regions. In this example, there's a thread attempting to read foo.x. This is a reference to a bar object in the source region. The read barrier intercepts this read, copies the object to the destination region, and also returns the new address. The copying process continues copying moving objects as well as doing read barriers if necessary until there are no longer any references to the source regions. At this point, the GC begins the reclaim phase. As you can see here, there are no longer any references to the source regions, so the garbage collector can free all of the RAM for these regions. And what we are left with is a heap that has much less wasted RAM compared to when the collection began. Now, you might be wondering, how much RAM can we save by compacting foreground applications as well as background applications? Well, the average heap size is 32% smaller compared to the Android N concurrent mark sweep garbage collector. And RAM loss to GC overhead is also a little bit smaller. One important factor about concurrent garbage collectors is how long application threads are suspended. Every millisecond that the threads are paused or suspended is one less millisecond to prepare the next frame for the UI. With the new GC, the average pause time is 0.4 milliseconds compared to 2.5 milliseconds in Android N. And the 99% worst case for large heaps is 2.6 milliseconds instead of 11 milliseconds in Android N. Finally, always compacting the heap has enabled ART to switch to a new thread local bump pointer allocator. This allocator is simpler and faster than the free list allocator it replaces. Overall, this means that allocations are around 70% faster compared to Android N, and if you go further back, allocations are 18 times faster than KitKat on a device-adjusted basis. And now, off to Nicholas for other optimizations.
Thank you, Matthew. So besides managing application memory, Art is also responsible for executing application code. And for every Android release, our team spends a significant time optimizing wherever we can. So in this talk, we want to share with you two major accomplishments we've made for this release. The first is a performance case study, and the second is about a new optimization framework for loops. Let me start with the performance case study, and then Art will later talk about loop optimizations. So to validate all the optimizations we do, we have our own benchmarks, where we look for regressions and improvements. But we also want to make sure that optimizations do matter for real Android apps. So for the O release, we have invested our optimizations on one of our Android applications, Sheets. Over the years, the R team and the Sheets team have worked on benchmarking the core computational logic in the Sheets app. Our Sheets benchmark suite is composed of three kinds of benchmarks: benchmarking low-level runtime capabilities, core Sheets formula evaluation, and benchmarks that shuffle random cells. And we're very excited to share with you that in Android O, we've made significant improvements to Arch runtime and compiler, up to the point that we are now running 8 out of the 9 benchmarks in Sheets from 2 times to 3 times faster compared to our previous release, Nougat. You may remember a similar graph than this one that we presented at the keynote 2 days ago. This is actually a snapshot of our benchmark monitoring tool, where we track over time the impact of each individual change we do in Art on our benchmarks. For this graph, what we see is that the Sheets aggregate score keeps on improving month after month between the two Android N and Android O release. So let me pick and explain to you the major improvements we've made for O. So one major change is, of course, the new garbage collector that Matthew just introduced. Overall, it improved the performance of Sheets by 40%, thanks to thread local allocation buffer and faster collections. The next major improvements we made is our inliner, which gave us another 20% boost. And this optimization was probably the easiest optimizations we've made, because we already had an inliner in N. But what happened in N is that now we're doing all the compilation in the background, and we only compile important things. So we can avoid the code bloating when we inline. With those two improvements implemented in N, it was a lot easier for us to do a more aggressive inlining for O. So for example, we now inline across DEX files, we inline methods which could end up throwing, and we give a much larger inlining budget, so more methods get inlined. So now let's move to an optimization that did require some work and helped us increase the Sheets code by 15%. That optimization is called code syncing. It's an optimization that essentially moves instructions next to instructions that actually use them. So typically what you want to do is instructions that are rarely being used, you want to move them closer to where they are used. So instructions that are not in the regular flow of your application, you want to move them to the exceptional cases. That's fairly abstract, so let me give you an example to make it more concrete. Here's an accept of Sheets code. There's a method called createRange, takes 2 integers, and returns a new range. The createRange method calls a helper method called checkCondition that will check the required conditions for creating a range. If those conditions are not met, we'll throw an error. Notice how the checkCondition is a var method. And this is important to notice, because it will affect the code that is being sent to our runtime. Here's how. So you start with a simple method. The Java compiler actually disugars the var args call to allocating a new object, allocating a new array, putting in an array boxed versions of start and end, and then passing this array to check condition. And this isn't Android specific. This is what the Java compiler does when it compiles to bytecode. And these instructions are not completely free. Yes, we made allocations extremely fast with the new garbage collector, but having to create this array and the boxed versions of start and end all the time the method is executed is not really ideal. So here's how we avoid executing it completely. First, we can easily inline the call to check condition. So internally, this is how the code is transformed in art. Notice how args now is only used in the if branch. So what the compiler can do is move the allocation and the boxing closer to where args is being used in the exceptional flow. So at the end of this optimization, what the compiler has made sure of is that only the required instructions will be executed in the normal flow. The last optimization I wanted to mention here is class hierarchy analysis. Class hierarchy analysis is a pretty common technique in object-oriented language. What a runtime will try to infer classes and methods that can be made final, even though they aren't marked as final. Having this information internally gives a lot of room for the compiler for more optimizations. For example, you can do more inlining. And because Java has dynamic class loading, we will bail out of these optimizations if suddenly a new class gets loaded, and all the optimizations we did by inferring final classes and methods become invalid. So this sums up the optimizations I wanted to talk to you about. For the record, we also did a bunch of other improvements for this release, such as faster type checks, faster access in compile code for classes and strings, faster JNI transitions, more compiler intrinsics, and a lot more where I did not have the space to list here. So for the interest of time, I'm not going to go into details on these optimizations. Instead, I'm going to hand it over to Art, who is going to tell you about a whole new set of loop optimizations.
Thank you, Nicholas. So if you don't look at virtual method overhead or general runtime overhead, programs tend to spend most of the time in loops. So besides all the good stuff that Nicholas already talked about, it can really pay off by optimizing loops specifically. And I will discuss some of these in this part. Optimizations really always consist of an analysis part where you look at the program and an optimization part where you actually perform the transformations. And you can see here like a list of all the work we did for O. But I'll only touch on a few of those in the interest of time. But before I do that, let's first look at what loop optimizations can do for you. So here you see a graph that plots Android O versus Android N performance, so higher is better. And the color encoding shows you specifically where loop optimizations in general, the blue stuff, has helped, and the red stuff where vectorization, which I'll talk about briefly, has helped. And you see that benchmarks on the left, like loop and sum, really get unrealistic high speedups. And it is really as a result of that we broke the benchmark. So we were able to transform loops into closed form expressions that execute really fast. And although that's always nice to have the ability in your compiler, it's not very realistic. But as you go to the right of the graph, you see more realistic speedups. Like LU and Linpack obtained like 10% improvements by vectorizations. So central to all loop optimizations is always induction variable recognitions. And that consists of finding expressions that progress in a regular and predictable way in your loop. And the most common example is a linear induction. So here in this example, the basic loop counter I is a linear induction, but also the expression j shown in blue is a linear induction. Every time around the iteration, it increments by a loop invariant constant. There's many more induction variables, and you see some of them depicted here in the graph. And detecting as many of them as possible is always good for the next phase, the actual optimizations. So let's look at what loop optimizations can benefit from induction variables. So here you see a somewhat synthetic example where the compiler can easily see that in the innermost loop, the increment to sum actually is very predictable. Since the loop only iterates 100 times, it can actually replace the sum, hoist it out with a closed form expression that just adds 100 at a time. After you've done that, you can actually hoist it again out of the next loop if you take a little bit care of the fact that the loop may not be taken when n is negative. So after that, the whole computation has been hoisted out of the loop, and the whole double loop can be eliminated. So in this case, the whole loop is replaced by a closed form. And that's one of the examples that I showed at the beginning where we broke the benchmark. Obviously, your code will probably not benefit this greatly from optimizations, but having this ability can really kick in like after you inline library code, not to the same degree, but it's still nice to be able to optimize your induction variables. Another example where induction variables can help you is with bounds check eliminations. So when you access an array, you always need to test to see whether the subscripts can go out of bounds. And if they do, you throw an exception. But if you know the exact range that induction variables will take, you can often eliminate those tests completely. So here you see an example that both the access to A and B will never go out of bounds. So the compiler can statically remove those tests, and the program, as a result, will execute a lot faster. Induction variables also tell how often loops iterate. So if you know that it is only a few times, you can actually completely unroll the loop. And the advantage of unrolling is that you completely remove the loop control overhead. It reduces the code size because you don't have the control to iterate. And it often enables like constant folding. So you see an example here where the blue part shows that the loop only iterates from 10 to 10, so it actually only iterates once. So you can replace the whole loop with a single statement, and as a result you can also constant fold the multiplication and already do that at compile time. So the program will run a lot faster. Again, typical code won't optimize right away, but after inlining or other forms of specializations, these situations occur and they can help improve your performance. So the last loop optimization I want to talk about is the ability of Android O to take advantage of SIMD instructions. So SIMD instructions are instructions that perform a single operation simultaneously to multiple data operands. So you see an example here where one instruction actually does 4 additions at the same time. And all our target platforms, ARM, Intel, MIPS, they have such instructions. And if you take advantage of them, it can greatly improve the performance of certain classes of programs. So converting sequential code, and we typically focus on loops, but it doesn't have to be restricted to that, into code that exploits the SIMD instructions, that process is called vectorization. And it's illustrated here where on the left you see a loop that iterates sequentially, and on the right you see the vector loop that actually goes by 4. And in order to do this transformation, this vectorization, you need some very specific analysis. You have to detect and resolve memory conflicts between the loop iterations to see if you can actually execute them in parallel. You may want to be a little bit more strict about alignment, because SIMD instructions often require stricter alignment on the memory. And you want to detect idiomatic constructs. We'll see an example of that shortly. Stuff that you cannot really express with single operators in your sequential code, but if you detect them, you can map them onto very efficient SIMD instructions. So let's just explore this whole vectorization with a case study. Suppose that you want to display a stream of pictures, like these paintings here in the graph, on your display, and you want to transition smoothly from one picture to the other. You don't want to just show one and then the other. You want to sort of have a transition in between. And you want to do that real time. You don't know the stream in advance. And of course, you want to do it in an efficient way. So one way to get a smooth transition is actually performing a crossfade. So what you do is, it's called a rounding halving add. So basically you take the average of two pictures and you show that in between the two pictures. So the example here, you see the shipwreck on the top and the quiet fire on the bottom. And the picture that you show in between will sort of be an average of the two pictures, showing them at the same time. It forms a nice, smooth transition. So how do you code it? And you don't want to go to a native solution. You don't want to use the NDK, you don't want to use GPU code. You just want to stay at source level. So here you see a method that could do such a crossfade. So you have two incoming byte arrays, which represent the pictures, x1 and x2. And you go through like a zero extension and an averaging operation, and then you compute the x out. So keeping this at source level is, of course, a much easier way of expressing such an algorithm. It's easier to write, test, debug, maintain, etc. You don't have to use the NDK, you don't have to use GPU code. So Android N will actually translate the loop that I just showed to the sequential code on the left, and Android O will now generate the SIMD code shown on the right. And I don't expect you to grasp this whole assembly right away, but just focus on the parts that have been highlighted. So first of all, in orange, you see that the sequential loop goes by 1. It does 1 byte at a time before it goes to the other one. In contrast, the SIMD code goes by 16. It does 16 bytes at the same time. The other thing that you notice is that the loop body is a lot shorter for the SIMD code. And that's a result of the yellow highlighted instructions. On the left, there's a lot of instructions required to do the zero extension and the rounding halving add. On the right, there's a single idiomatic instruction that can take care of that. So all this combined makes sure that the loop runs about 10 times faster if you just look at the loop. However, if you look at the real application, where this loop is actually part of a larger thing, where there's like a handler requesting new pictures, etc., you can see that vectorization made a difference between rendering at a slow 20 frames per second, and after vectorization, we render at 60 frames per second. And that's actually as fast as you can go. Like, you cannot render much faster. So that really shows that vectorization has given you the power to render at a very acceptable speed, and you actually have CPU cycles to spare, because it doesn't need the full power to go to the 60 frames per second. And all this was made possible by the vectorization. You don't need to write like tedious NDK code anymore. You can just express the loop at source level.